Polynomial and rational inequalities are the next step after considering linear inequalities. For linear inequalities, we just solve for the variable, and that gives us the solution set. But polynomial and rational inequalities, it has a little bit more to it that we need to do. First off, we need to find the boundary points. These are the locations where the function can shift from positive to negative. It doesn't necessarily do that, but if it is going to change from positive to negative or negative to positive, it will always do it at the boundary points. So we need to find those points. And for functions, the boundary points are where the function crosses or touches the x-axis or has an asymptote there. And this is naturally the same idea as finding the zeros of the function. So that's what we're going to do to solve these things. We're just going to try and find the zeros of them. And doing that, we'll be able to find the intervals that the function can potentially be, therefore finding the solution sets. So here's my first polynomial inequality. What we're going to do here is we're going to get everything over to one side. And this is different, like I said, from the linear inequalities, which is where you just solve for x. You can't just solve for x in these. That's because we have both x and x squared. And there's no real way of solving for just x in just a regular solution, like just moving things over and dividing by things and all that stuff. You have to do a different solution method. It just won't work unless you do something different. So I'm going to add x squared and subtract 6 to get everything over to one side. I'm also going to combine these two at the same step. That's going to give me x squared, then minus 6 minus 5 is minus 11x. Plus 30 minus 6 is going to be plus 24. This is greater than 0. Now, this should look familiar, right? This is kind of like ax squared plus bx plus c equals 0. It's not the same, but we can solve it in a similar fashion. We can factor it, thereby finding the zeros of this polynomial and going from there. Let's try the AC method. A times c is 24, b is 11, sorry, negative 11. Two numbers multiply to 24, add to negative 11. That's going to be negative 8 and negative 3. Since a is 1, we can immediately factor this down into x minus 8, x minus 3, greater than 0. And so we can find our boundary points quite easily from this. It's where the function is 0. From this one, we get x equal to 8. So 8's a boundary point. And from this one, we get x equal to 3. So 3 is a boundary point. Let's graph this thing and see what it looks like. All right, here is our function graphed. I showed I graphed them both ways. They're the same function, so you really don't need to show both or write both methods there. I'm just going to use this first one, but they're the same thing, the factored form and the regular expression. But this is what we have. Of course, it does touch the x-axis at the zeros that we found, 3 and 8. And you can see that on the left-hand side of 3, we have the function being positive. On the right-hand side of 8, we have the function being positive. And everything between, the function will be negative. So that's kind of our intervals here. We have negative infinity to 3, then 3 to 8, and 8 to infinity. And you can see from negative infinity to 3, we have the function is always above the x-axis here. It just keeps going up and up and up. From 3 to 8, everything is below the x-axis here. And finally, from 8 to infinity, everything is above the x-axis. Okay, here's the intervals again. If this is our function here, f of x equals this thing, then from the first interval, we have f of x is greater than 0. That's where it was above. Then this portion, we had f of x is less than 0. And finally, we had f of x is greater than 0. And so for our function, or our inequality, I should say, we're asking when is it greater than 0? That's going to be in this interval and this interval. Therefore, our solution is going to be from negative infinity up to 3, unioned with 8 to infinity. Now, you see I'm using parentheses here. That's because we have a strict inequality right here in the yellow. This is a strict inequality. If it were, greater than or equal to 0, then we would include the boundary points. Of course, you never include infinity, only real numbers. So that's how you can solve it. You can always find the boundary points to split up the intervals into these three sets here. And then you can just look on a graph, or what I'll show you next is where you test the intervals. Okay, here's another polynomial inequality. I'm going to get it everything over to one side, so I'm just going to add the 7x. That gives me x squared plus 7x greater than or equal to 0. And factoring this is quite easy. All we have to do is take out an x. All right, and at this point we have the boundary points already. Boundary points are going to be 0 for when, let's see, this one is 0. That's 0 when x is 0. So the first boundary point is 0. The next one is going to be -7. And what I like to do is draw out a number line and then draw these points, -7, 0. So what I'm kind of drawing here is the x-axis of the graph. And then, so I'm really just looking at the domain of the function. And so that's what we're kind of considering here, is what portions of the domain give us the function greater than or equal to 0. So we have these three intervals here. We have this first one, this one here, and finally this last interval from 0 to infinity. Now we just need to test the intervals, and a way you can test it is by plugging it into this factored form. So let's plug in a number in each one of these domains. I'm just going to choose some random ones. Let's do like -10, -1 seems easy to test, and 1. Every number in these intervals will always have the same sign as a result. So you don't need to worry about testing multiple numbers in them, just one of them. So let's test these numbers. We have, let's see, I'm going to plug in -10 here. Then we have -10 plus 7. So once again, I'm just plugging it into this, green here. I'm just plugging it into this thing here to see if it's greater than or less than 0. So we have -10 times 10, -10 plus 7, that's going to be -3. -10 times -3 is +30. So we know that in this yellow interval we have positive numbers. It's always positive. Now for the next one, we can just replace the -10 with -1. I should just erase the 0, I suppose. That's going to give us -1 times -1 plus 7 is 6, which gives us -6. So that is negative in that middle orange interval. All right, last one. We're going to test +1. So we have 1 times 1 plus 7 is 7, or no, it's 8. 1 times 8 is 8, and that is positive. Typically, you'll see this where a polynomial function will change from positive to negative to positive. This is not always the case, so don't rely on this, but this is pretty usual. So you can kind of expect it. You would rarely expect two of the same signs, but it does happen. All right, we are looking for when the interval is greater than or equal to 0. That's here in the green, greater than or equal to 0. Therefore, when is it positive? And that happens in the yellow and the blue. The yellow interval is from -infinity up to -7. And the blue interval is from 0 to infinity. Now this is technically wrong because this is greater than or equal to, so I do have to include the boundary points. So make sure that those are square brackets, not parentheses. All right, this one's already solved for 0, so we can just go ahead and factor this thing. We have a times c is 25 times 1, 25, and b is -10. Two numbers that multiply to give 25, add to give -10. That's just -5 and -5. A is not 1 here, so let's do the whole AC process. -5x minus 5x, and then plus 1. Of course, that's splitting up the -10 into those two numbers we found. And that's going to give us, factoring by grouping, we're going to get x And then we're also going to take out a 5 from the first two numbers, right? That's going to give us 5x minus 1. And from the next two terms, I only see 1. And because this middle sign here, let me just highlight it here. Because that's a negative, I'm going to take out a negative 1. That's going to give me 5x minus 1. And now, of course, I can factor out the 5x minus 1 from both of these terms. That gives me 5x minus 1 from the factored out. And from the outside portions, we get 5x minus 1. So it's the same thing actually twice. Now, what's the boundary points that we get from this? Well, from this first one, 5x minus 1 equals 0 when, well, 5x minus 1 equals 0. Add 1. Divide by 5. And you see we get 1/5. Of course, this one's also going to give us the exact same answer. So x equal to 1/5 is the only boundary point. All right. We have 1/5 here. So we only have two intervals that we need to concern ourselves with, and we need to test these guys, see what we have. It's just 5x minus 1, 5x minus 1. So let's test. 0 is probably going to be very easy to test, and then 1 is probably way over here. Let's test those two things. So we have 5x minus 1 times 5x minus 1 is really just 5x minus 1 squared. I'm just going to plug in our numbers into this. 5 times 0 minus 1, 5 times 0 is 0, minus 1 is negative 1, negative 1 squared is positive 1, which makes this interval positive. Plugging in positive 1 into there. 5 times 1 is 5, minus 1 is 4, 4 squared is 16. And that is also positive. So this is one of those types where you see there's two of the same sign right next to each other. And we're looking for when is this whole thing less than 0. Well, less than 0 is when it's negative, and there is no interval here where it's negative. Therefore, we have no solution. Really quick, I just want to show you this on the graph. So let's look at that. So here's the function on the graph. You see that it just touches the x-axis right here at, this is the same thing as 1/5. And as you can see, the function is always positive. It's always above that, except for at that one point where it equals 0. So when is this function less than 0? It never is. It's never down there. That's the reason why we only had one boundary point, because it just touches the x-axis rather than crossing it. Before I move on, I wanted to talk about if this interval was instead less than or equal to 0. Well, that would change this interval right here to being less than or equal to 0. And what we're asking now is, when is this thing 0 or negative? It's never negative, but it does equal 0. It equals 0 only at one spot, namely the boundary point, 1/5. So we would not have no solution in this case. We would actually have only one solution, the single number in the set of 1/5. And you have to write that as a set because it's not an interval, it's just a single number. So you use set notation to designate that. You can't use a coordinate, it's not that way, it's just a set of 1/5. Okay, for this one we have a third degree polynomial, and we don't have any other piece of information, so the only thing we can really try to find the boundary points here by algebraically finding it is by factoring by grouping. So let's try that. Let's look at the first two terms. In the red we have, I can take out an x squared. That's going to give me x plus 4. And from the blue I can take out a negative 1, which gives me x plus 4. So that worked out. I can take out an x plus 4 from both of these terms. That's going to give me x plus 4 times the outside is x squared minus 1. This, of course, is greater than or equal to 0. And x squared minus 1, this is a difference of two squares, so I can factor it down into the first thing being squared plus the second thing being squared, which of course is 1 squared. And then the first thing being squared minus the second thing being squared. So x plus 1, x minus 1. And you see we have 3 zeros here, which is what you'd expect, right? This is a 3rd degree polynomial, so we would expect 3 zeros. We get the zeros, which are the same thing as the boundary points. Is going to be -4, -1, and +1. So that's going to split up our interval into our graph into 3 intervals that we want. Or sorry, it's 3 boundary points, so it splits up into 4 intervals. And they look like this. Blue, and finally the green here. And so what we can do is we can test the intervals, right? I could test 0. I could test -2. Put them on top here. 0, -2, maybe like -10 or -5. And then what I'm going to show you how to do is what I like to do is just think about the signs. Don't think about the number. The number doesn't matter here. All that matters really is the sign of it, because that tells us if it's above or below the x-axis. So I'm just going to test some very large number like +1 million. The number itself doesn't matter. It's just if it's very, very large, then we can assume some things about it. So testing the x plus 4, right? X plus 1 times x minus 1. I'm going to test +1 million to show you how that's done. So just think of x as a very, very large positive number. So it's going to be plus 1 million, plus 1 million, plus 1 million. The first term here, the first factor, this is definitely positive. A very large positive number plus something, that's going to be positive. A very large number plus something, once again, is going to be positive. A very large positive number minus a very small positive, minus a very small positive number is still going to be positive. You're not going to change the sign of that. So what we really have here is a positive times a positive times a positive. That's going to make the green interval positive. And you can always use that as long as you're on the 2 edge cases, like the yellow and the green intervals here. We can always use a very large or very small, or very negative, I should say, number. So I'm going to test -1 million now and show you it's the exact same process here. So you have -1 million, -1 million plus 1, and then -1 million plus 4. So from this first interval, we have a very large negative number plus something very small. That's still going to be negative. Very large negative number plus 1. That's still going to be negative. And a very large negative number minus a positive number. That's going to make it even more negative. We get negative. Negative times negative is positive, and positive times negative is negative. So you see here we have the 2 intervals without having to compute numbers. Once you get really good at this, you don't even need to kind of plug the numbers in. You can just kind of do it in your head. You can see it, how it all works. But that's how I would do it for the end sections. For the middle ones, I mean, 0 is very easy to test, right? You just plug 0 in there. You get +4 times +1 minus 1. That's 2 positives and a negative. That's going to make this interval negative. And I'm sure you can kind of guess what the orange interval is going to be. But just to show that, let's plug in -2. -2 plus 4 is 2. -2 plus 1 is -1. And -2 minus 1 is -3. 2 negatives cancel. These are all positive now, so it is indeed positive. So in this case, we do have that flip-flopping sign change. So that's what we can use that to find. I guess I'll just put in yellow again. When is this thing greater than 0? Greater than or equal to 0, I should say. That's going to be in the orange interval, which is -4 up to -1. But we're going to include the boundary points, right? It can equal 0. This is going to be unioned with 1 up to infinity. And that is our solution for this inequality. Rational inequalities are done the exact same way as polynomial inequalities, except now we need to consider both the zeros from the numerator, which are the zeros of the function, and the zeros from the denominator, which are the asymptotes of the function, because both of them have a potential for changing the sign of the function at those points. Once again, though, you do have to understand that it's not necessarily going to change the sign. It may, but sometimes it actually will keep the same sign. It depends on how the numbers are played. If there's like a square or a fourth power or some even power in there. Okay, we're going to factor everything. This one's pretty easy. It's pretty much already factored. So all we really need to do is figure out what is the zeros from the numerator and the zeros from the denominator. From the numerator, right, we have 4 minus 2x equals 0. Add 2x I should say, and then divide by 2, giving us x equal to 2. That's our first boundary point. The next one's going to be subtract 2, then divide by 3. We get x equal to negative 2/3. And this is what we can use to test the different intervals. We have positive 2 and then negative 2/3. So once again, 3 intervals. And we're looking for when is the function less than or equal to 0. So we do need to include the boundary points, except for one thing here, which I'll talk about in just a minute. Let's test these. We have 0 on the inside. Always test 0 if you can. It's a good number to test. A very large positive number and a very large negative number. And we haven't really changed anything, factored anything, so I'll just write this thing down again. 2x over 3x plus 2. Okay, if we test a very large negative number, well, right here we have a negative times x, which means a very large negative number times a negative is going to make it a very large positive number. So on top, this is going to become positive. On bottom, we have a positive times a negative is going to be negative, and then plus some very small positive number, it's going to stay negative. If this is at all confusing to you, just test a number, like for instance, -1. -1's not too hard to test here. Just plug -1 into this thing, calculate it out, and you're going to see it's going to end up being a negative number. So the first interval is going to be negative. Let me do that in red here. Okay, the second interval, let's plug in 0. 4 minus 0, so it's just going to be 4 over 3 times 0 is 0 plus 2. And we get a positive number here. All right, last one, we're going to test a very large positive number, so some very large positive number here. On top, it's going to end up making it negative because -2 times a positive number is negative. And adding on some small positive number like 4 is going to make this whole top thing be negative. On bottom, we have 3 plus 3 times a very large positive number is going to be positive, plus 2 is going to be positive again. And this gives us a negative. All right, that's negative. Now, if we look at what we want again, we want less than or equal to 0. So we're looking for the yellow and the blue intervals. The yellow is going to be from -infinity up to -2/3, unioned with 2 up to infinity. Now, we do include the boundary points, so we would say this. However, there's one issue here, and that is because we have a denominator. And the denominator can never equal 0. Therefore, the 0 from the denominator, this one here, must always be excluded. You can never have x equal to -2/3 because then we have a division by 0, which we can't have in mathematics. So this negative 2/3 has to be excluded. It has to be a parenthesis next to it. But the positive 2 is allowed because it's a 0 from the numerator, which is just 0 divided by something, which is just 0. It does in fact work. So make sure when you're doing rational inequalities, you keep in mind that the denominator can never equal 0. Therefore, if you have an inequality like this where it's not strict, then you need to always not include the zeros from the denominator. I hope that makes sense. I just want to graph this one real quick so you can see what it's kind of looking like, what we're dealing with here. This is our rational function. You can see if I make x equal to negative 2/3, that is the asymptote here. You can see that's where the graph is asymptoting to. That's why it's called an asymptote. The coordinate 2, 0 is the 0 that we found, which is where the function changed from positive to negative. So yeah, that's the kind of intervals we have here. We have this interval, negative infinity up to the negative 2/3. Then we have this very small interval here, right, where the function is positive from negative 2/3 to 2. And finally, from 2 up to infinity is where it's negative again. For this rational inequality, we're going to move one of the fractions over to the other side. So let's subtract the 6 over 6 minus x to the left-hand side. You don't have to always move it to the left-hand side. It's just, it tends to be easier to think about it that way, for me at least. Now, we need to have a single fraction here. In the previous problem, we had just a single fraction. It's just easier to work with as a single fraction. We need to combine these things. In other words, multiply by the least common denominator. And that's going to be x minus 6 times x plus 5. I'm going to multiply each one by the other denominator. On top, I'm going to distribute the 6 into there. The same thing with this 6. Also, this negative needs to be distributed in there as well. So that's going to give us 6x minus 36. And then what you can do is, let's actually think of this as, instead as 6 times x plus 5. And then this negative goes to that and becomes negative 6. And that gets distributed. So now we have negative 6x minus 30. This is all over x plus 5, x minus 6, which we're going to leave factored. We're not going to undo that factoring. On top, the 6x and the 6 and the negative 6x cancel. Negative 36 minus 30 is going to be negative 66 over x plus 5, x minus 6 greater than 0. And we only have zeros in the denominator. So that's going to be x equal to negative 5 and positive 6. These are, of course, our boundary points. And we know that because they're from the zeros from the denominator, that x actually cannot equal negative 5 and 6. Just keep that in mind in case we need to do anything. This one, we don't really have to worry about that because the inequality is strict. We can't include the boundary points. But now we have our intervals, negative 5, 6. We have these 3 intervals. Let's graph this one and see what the solution is. All right, here is our function. If I zoom out a little bit, you can see a good depiction of what this graph looks like. We found that x equal to negative 5 and x equal to 6 were asymptotes. And you can see that is indeed where the function changes from negative to positive. You can also see that because the power of the top, which is 0, because there's no variable written, and the degree in the bottom, which is 2, since we have x times x. The degree on top is 0, the degree on bottom is 2. That means it has a horizontal asymptote at y equal to 0. So this function will never cross 0 again. In fact, it actually never crosses 0 at all. And so we can know that these are the only 2 places that it will ever shift. I mean, we found that anyway from the border points, but that's just another affirmation of what we're doing. And we can see on this side, everything less than negative 5 the function is always negative. It's always below the x-axis. On the central interval from -5 to 6, the function is always positive. And then finally, from this interval 6 to infinity, the function is always negative. So we have these three settings, negative, positive, negative. We're looking for when is the function positive, and that's only in this central interval. The border points are zeros from the denominator, so we can't include them, but we wouldn't include them anyways because this is a strict inequality. So that is our solution. All right, let's go ahead and factor the top and bottom. We have -5 and -4, which is going to be -5 plus 1. And that factors the top because a equals 1 here. The same thing is true for the bottom. We have 18 on top and a -9. That's going to give us -6 and -3. So on top we have x minus 5, x plus 1. On bottom we have x minus 6, x minus 3. Our border points then are going to be at, on top we have 5 minus 5 is 0, -1 minus 1 is, or -1 plus 1 is 0, 6 minus 6 is 0, and then 3 minus 3 is 0. So those are our border points. And of course, we have 5 border points, so we should expect 6 interval. We have 4 border points, so we should expect 5 intervals. 1, let's see, we'll do 3, maybe like 5 and 6. It could be a little bit skewed, but whatever. So this one, this interval, this one, and I'll go back to yellow again. All right, you can test a few numbers. We have 0 here. I can test 4 here. I can test like 5.5. Very large positive number. You can test like -10 or +10 and -2. Let's graph this one and see what the different portions are. All right, here's our function. I've plotted the zeros, -1 and 5, and the asymptotes, 3 and 6. And this is what our function looks like. It kind of does this. This is pretty much a typical rational function in my mind. It normally looks something like this. And you can see from -infinity to -1, we have the function is positive. From -1 to 3, the function is always negative down here. Then from 3 to 5, the function is always positive, just asymptotes upwards. From 5 to 6, very small interval here, this just goes all the way down to -infinity. And finally, from 6 on up, the function is always positive. The degree on top and bottom are the same, which means that the horizontal asymptote for this guy is going to be y equal to the ratio of the leading coefficients, which you see here is 1 over 1. So y equal to 1 is the horizontal asymptote. Y equal to 1 there. Let me do a different color rather than the red, purple again. So you can see the function gets closer and closer to that horizontal asymptote on the left and on the right. And so we know that this side here will never cross 0 again, so there's not going to be any other border point there. All right, these were the signs that we found for the intervals. We're looking for when is it greater than 0. So we don't have to worry about border points or having to exclude the denominator equal to 0. All we have to do is find the actual intervals, which is going to be 3 of them. We have -infinity up to -1. That's the first yellow interval. Unioned with 3 up to 5. That's the blue interval. And finally, union with 6 up to infinity, the rightmost yellow interval. And that's our solution for this problem.